Okay. Good afternoon. Let's make a start. Is it okay if I don't use this microphone? It's just annoying. It just keeps on tapping. Is it okay? Can you all hear me? Yeah? Okay, let me just increase the volume a bit. Right. Okay, so we're going to carry on with chapter 2 now. I made a quick start last week, and I spoke about work and heat, and I said this is really the chapter where we start to look at real thermodynamic stuff. So we're going to move away from the fundamental, not fundamental, but like sort of the basic concepts like pressure, velocity, density, things like that we covered last week. And now this is where we really start looking at thermodynamic theory and laws. So I explained that work and heat. Actually, I think I'm going to use this microphone. Ouch. It's all right. We just need to increase the beats extra. Okay, so what I explained last week was that we have two concepts of work and heat. We're going to start with work today, and I think next on Thursday we're going to cover the heat. The formal definition of work is when you have any motion against an opposing force, that would create some sort of work. And we're going to look at the different types of work that are available to us. And of course, heat is just the conversion of energy from one source to another, really. It's just, the conversion of energy is what defines heat. Now, I also explained that this is the equation that we're going to be using for the first law, which relates the internal energy to heat and work. And, of course, you could divide both sides by mass, and then get the specific energy equals to specific work and a specific heat. But we'll come back to that later on. The next paragraph was about the fact that we do not use the same symbol mathematically in terms of mathematical representation. We don't use D across the whole equation. For Q and W, we use delta. That just to indicate that work and heat are not properties, whereas U is. And therefore, we can use D for U, but delta for Q and W. And then the explanation, mathematical explanation, really is here. And I ended up by just saying that the work done by a system, and I've put by in bold, we're going to see why, when the sole effect on everything external, or the surrounding, will be raising of a weight. So any work that you see can be converted, or you can find the equivalent of that work by lifting or dropping a weight. That's just what that really says. On the next page, I'm going to be looking at 4 examples. These are 4 very simple examples, but as you'll find out, there are fundamental differences between the first 2 and the second 2 examples. The whole point of the next 2 pages is really to tell you what is negative work and what is positive work. And you may not really care about at this stage, or you might think, well, that's not really important, but when we do some examples, you see actually that it makes a huge difference, because at the end of the calculation, when you find, for example, that the work is equal to 40 joules, if the work actually was negative, then it should be minus 40 joules. And actually, when the equation becomes even more complicated, or when the problem becomes more complicated, if you don't take the sign into account, then you will miscalculate the overall work on heat in the system. So it is important to get the convention right, and I mean convention because, as I mentioned, some of the textbooks would use exactly the opposite convention. But what is good is that in this module, we're going to be consistent, And in fact, for the rest of your degree at this university, we're going to be using the same convention. So you don't really have to worry about that. It's just a matter of when you come across some textbooks, if you saw that the work actually is defined now negatively as opposed to positively, then just don't be confused. So let's just think about these examples. In any of these examples, you have two parts. One is a system, and one is a surrounding. And you have to be very clear on what justifies or what defines the system and what is actually the surrounding. Now, the job actually here isn't that difficult because you even know what the system is. Normally, the system is what you are interested in. And of course, in other occasions, maybe the falling weight would have been interesting, but because it's thermodynamics and you're interested in heat and work and things like that, then obviously this is what you're interested in, and we call this the system. Anything outside the system will be your surrounding, and that completely makes sense. Now, in this case, and in other cases, the other part of this, for example, in this case, you've got a falling weight, and you've got a weight which is on a flat surface. I'm going to call this the surrounding in this case. This represents my surrounding. Now, if I were to ask you, which one of these two, either the system or the surrounding, which one is it now that is doing some useful work? Which one is actually sort of pulling the weight, as it were? It's the surrounding, isn't it? Because the system is just there, it's not doing anything. It's the poor surrounding that is just pulling the weight and moving the system. So, by our convention, in this situation, the work is negative. This definition refers, so our reference is a system. We don't, at this stage, care about the surrounding. What I mean by negative work, I mean that the work in the system is negative. Let's just, for now, put minus VE, which means this is negative work. Let's just move on for a second and move on to the second example and see what this case represents. So here, it's not clear, but this is our system. This is it could be a tank, and a fluid is inside, and then you've got a weight which is falling, and that would result in rotating this propeller. And so again, if that tank and the fluid in that tank is your system, which one of these? Is it the system that's doing some useful work, or is it the surrounding? Let's think about it. So, is the propeller rotating itself? Or is it actually the falling weight which is causing that rotation of the propeller? Is the weight, isn't it? So, if this is your surrounding, then actually this is the one that literally is just pulling the weight, really, is doing some useful work. So as far as your system is concerned, again, similar to the first example, you have some negative work. Again, make sure that our reference is a system, not the surrounding. What we care about is the system. So, to identify negative and positive work, that's obviously very important. And by looking at these examples, you'll see which one is doing some positive work, which is doing negative work. The other aspect, which is a bit annoying, but still you have to think about it, is the way that we write it actually in a written sentence. And it's the use of the word or the term by or on. And you see, you've got by, on, etc. in the text. The reason why, apart from finding out and understanding which one is doing positive work and negative work, it's also important to find out, when I say that the work is done by the system, then you understand what that means. And when I say the work is done on the system, then you also appreciate what that means and whether that justifies positive work or negative work. So, what I would say about this example is that the system now, if you want to read this sentence now, it says, energy entering the system in this manner is defined as negative work done by the system or positive work done on the system. So, in this case, the work by system is negative, but the work on the system is actually positive. And this is the bit which I don't like, and it's a bit confusing. But the reason why it's important to understand this is because you come across sentences which doesn't tell you, which doesn't explain the situation, but rather it gives you that description of by and on surrounding, a system, and therefore that's important to understand. In this example, actually, if you look at the surrounding, the work by the surrounding is actually positive, and the work on the surrounding is negative. And of course, they always have to be the opposite, because one is doing the work, what the other one is not doing the work. Therefore, these sides have to be the opposite. And what I would say here, if it really helps, is that when the system, the work by the system is negative, then really the work in that context is negative. Therefore, this is the sign. Out of these 4 signs, this is the one that really matters. Now, however the sentence is defined and is written, as long as you can understand what is the sign when it comes to the work by the system, that justifies the actual sign for the whole combination. Now, let me just now move on to the other 2 examples. These 2 actually examples of positive work. Now, in this example, we've got a battery. This is our system. This is a battery. And when we switch on the switch, when it's activated, then this electric motor will work and it will lift this weight. So again, thinking about which one is doing the work. So this is the system, this is the surrounding, if you like. Who is actually doing some useful work here? It's a system, isn't it? Because the surrounding is just a byproduct in this case. It's just really is on the passenger side, if you like. It's not doing anything useful. And as a result of that, this has to be positive work. So the work by the system is positive, and the work by the surrounding is negative. So if you'd like to, again, write those, if this is the system, the work by the system is positive, on the system is negative, and in terms of the surrounding, the work by the surrounding is negative, on the surrounding is positive. And whatever way you want to define this in the written English, then that's the convention we use. And the last one is you've got a bag, and this bag inflates. It doesn't matter how, we don't care really how this bag inflates, but as soon as this bag inflates, then it will lift this weight. So if this is your surrounding now, you see that the system is actually doing the useful work, and therefore that is positive work. So you've seen now 2 examples of negative and positive work. Something to sort of make this maybe a bit clearer is that this is now about gaining and losing energy. So if the system, and remember the system is really is our reference. If the system gains energy, or if the system loses energy, now I want you to tell me, when the system gains energy, is that positive or is that negative work? Who says negative? Okay, majority, yeah, that's correct, yeah, exactly. Okay, so now And of course, when you lose energy, when the system loses energy, then it's positive. So now, I'm glad actually it makes sense. And you can see that very clearly in the examples here. I think one very simple example, if I wanted to tell you, is if you are just sitting on the couch at home and somebody is actually cooking for you, whether it's your friend, your flatmate, girlfriend, boyfriend, whatever, if that person is actually cooking for you, that means you're not doing anything. You're just sat on the couch and doing nothing. So that person is actually losing energy. And if you're the system, then you are actually, by eating that food, you're getting energy. Okay? So if you're the system, then you're not doing any work, therefore your work is actually negative. And that sort of makes sense by looking at the convention here. Okay, so let's move on. Here I'm talking about quasi-static process. In a lot of situations, we're going to have quasi-static processes. Again, it's one of those assumptions to make life easier when it comes to definition of the theory in thermodynamics. So it's important to understand why we would be dealing with quasi-static. Now, static makes sense to you. You know when something is static means there's no movement, there's no change, it's static. When we use quasi-static, it just really defines it's almost static, if you like. And that doesn't mean, because if you just say this is a static process, that means nothing, absolutely nothing is changing. But if you say it's quasi-static, then you just give yourself a freedom that some of the things might change, but as far as the whole general picture is concerned, it's actually an equilibrium system. So, what is the formal definition? Quasi-static change in a system is change that takes place whilst maintaining equilibrium. On the practical side, this means that the change does happen, but it happens at a very slow pace. So it's done very slowly. I referred to the fact that we have to be looking at slow processes in the first chapter because I talked about, for example, when you were inflating a balloon, and I said if you just inflate it too fast, you're introducing turbulence. And turbulence, because of its random and very unsteady nature, then it would be quite difficult to apply lots of equations. And therefore, we assume that that inflation process takes a long time and it's done very slowly. The same here. Now, I want to talk about equilibrium and just mention that there are, as far as this module and this chapter is concerned, we could potentially define two different types of equilibrium. One is the mechanical one, which is these two examples. These are the mechanical equilibrium examples. And the other two are the thermodynamic equilibrium examples. Let's start with the mechanical. In definition of equilibrium, the role of the external forces is very important. And it defines whether you are in equilibrium or not. If you have external stimulation, which means you've got some sort of external force outside the system, then you definitely do not have equilibrium. So if there is external force, you do not have equilibrium. That's just, it's logical. If there's no external force, actually it could be no equilibrium, or actually it could be equilibrium. And we'll see actually why in this case. So when there's an external force, so something is actually moving this. So this here, what we have in this example, we've got a you can assume you've got a sort of a cylinder or a container, and you've got this ball in this cylinder, and that sort of defines the system. If this ball is moving, maybe there's some sort of physical movement or stimulation outside this box or this coordinate. Therefore, you do not have equilibrium. That's absolutely clear. If there is no external, but there could be something within the system, that actually would be the case, would be either equilibrium or not equilibrium. And you can see the examples here. In the first case, there's no external and there's no internal forces, and therefore you have mechanical equilibrium. In this case, despite not having any external force or stimulation, it's not an equilibrium because there is, for example, maybe the walls are flexible, maybe. You've got sort of a bouncing walls, and maybe this wall, this sort of floor, is actually frictionless as well. So this, even though you do not have any external force or stimulation, because of the mechanical properties or boundary conditions that you've got in this problem, you do not have equilibrium. So that's why I gave you these two scenarios. When there's in the absence of external forces, you could have both scenarios depending on the situation. Exactly the same story when it comes to thermodynamic properties. So a typical example in thermodynamics is a cylinder and a piston, and if you've got certain pressure and temperature in this cylinder, and there's no external stimulation, then you can assume that you have equilibrium. On the other hand, if you've got some sort of, if you had some sort of pressure waves, these pressure waves inside the cylinder, or you had some sort of chemical reaction, for example, inside the cylinder, so everything is actually done within, is inside, there's nothing external, but still you do not have equilibrium because of that change within the system. Now, this is really the summary of what we've been saying about positive and negative work, and it's also about gaining and losing energy. So this is really just a summary of what we've said. There's nothing new in here. And this rather confusing figure really is just trying to say that by gaining energy or losing energy, is, somebody could see that as a positive or negative work, and therefore it makes sense why different sources would treat these conventions differently. We have an example of the Rogers and Mayhew, which uses the opposite sign convention, but again, that's not a concern, and we're not going to sort of talk about this any further. So we're just going to be consistent throughout, and that's what is important. Let's just do one example here, and then that shows the importance of using the right sign convention as far as we are concerned. So, the force needed to slowly compress a nonlinear spring. So we've got a spring, like that. And this is your system. And you've got some external, some compression force applied to this nonlinear spring. And this compression is given by this expression. So the force here is defined by this equation. And in fact, it's a function of u. U in this case, and actually for the rest of the chapter, doesn't represent velocity. It represents displacement. So displacement is actually measured from the origin. Whatever you move, we call that u. And so determine the work done by and on the system, along with the work done by and on the surrounding, in compressing the spring by 0.6 meters. So if the spring moves by 0.6 meters, we want to find out what is the work done on, etc., by the surrounding and by the system. The first thing we realize is that because the spring is your system, and the spring itself is not doing anything. It's actually an external force compressing it. Therefore, the work by the system has to be negative, based on what we described so far. And equally, and oppositely, the work by the surrounding would be positive. But it's mainly this one. When I said the system is our reference, it's because we mainly care about what happens to the system as opposed to the surrounding. And therefore, this is really the main sign in here. When you do more examples, actually this becomes quite natural. So I'm focusing so much on the sign convention and everything else now because we just introduced that. But really later on, it just becomes quite natural. So don't worry about this, and I personally am not going to be playing with these words like what is the work done by, etc. I know it's a bit nonsense. Therefore, if I want to ask you a question, I'll probably define the problem as opposed to playing with these conventions. So, the increment of work done by the system is given by this. And we'll see actually why, because on the next few pages, we'll be talking about the work done and how it's related to displacement and force. But as for now, assume that the work in this case is force times the change in displacement. And of course, all we've been saying here so far about the convention shows itself in this sign here. Because what you know is that generally work is equal to force times displacement. But why do we have this negative sign here? It's just because exactly for the reason why we established that work by the system here is negative. Okay, so let's just move on and look at the equation. So naturally, because this is a nonlinear spring, you've got to do integration on the equation. And so let's just write the work in terms of force and displacement. And I'm just going to replace F by the equation which we've been given here. So that is F. And of course the limits on the integration is from 0 to 0.6, because 0 is at time 0 or time 1 if you like. You start with 0 displacement, and at the end of the process your displacement is 0.6, and therefore you have these two limits on the integration. Once you do the integration, you end up with this equation, and then you put the limits in there, and you get minus 37.3 joules, and that's how much work is done by the system. So the only thing I mention here is really that when you start adding up the work by the system and the work by the surrounding, of course you have to get 0 because of the first law and what we mentioned about the fact that energy is really conserved, and it just really moves from one form to another. That's really as simple as that. And this is just a very simple example of why and how we use this convention. On this page, we are really talking about, we really start looking at work and different types of work that you could encounter. So let's just start with two types of work, mechanical and displacement work. These are not the only types, but for now let's just focus on these two, because these are the most common ones. Mechanical work is a type of work that you've been studying in physics, in A-levels, and in mechanics. So I'm not going to spend a lot of time on that. It's just to say that really the work is the dot product of force and the displacement. And when you have something in bold, remember the convention. This represents a vector, and that's why it's actually it's a bold. And the other thing I would say is that if you think about the main axis, I know you've covered this before, but I just want to make sure that you know that this is really I, J, K. Also X, y, z. And of course, sometimes when it comes to velocity or displacement, then you have u, v on w. This is just to make sure that you understand that these mean the same thing, it's just with the mathematical representations of the three axes. And of course, when you do the dot product, this is not absolute value. This represents magnitude. So it's the magnitude of force times the magnitude of displacement times cosine theta. And if you want to see this graphically, really, if this is your du and this is your force vector, then that component here is really f times cosine theta, if this is theta, the angle. Just going to zoom in so that you can see clearly. So theta represents the angle between the force and the displacement, and this component here is really force times cosine theta, what you have here. But anyway, that's not really what we are covering here. You've already covered that before, so I'm just going to skip that. This relatively odd figure is something that you're going to see at least 3-4 times in this module. So it's important to understand what this represents. This is, in a way, this could be a balloon, I think. That's the easiest way to explain that. But in a way, that represents the work. This represents lots of things. This could represent displacement. So just bear with me when I'm explaining this terminology and this configuration. So assume that this is a three-dimensional spherical or whatever shape 3D balloon. And of course, you've got the surface. And of course, you've got the volume. So that's the first thing. We normally look at a small opening, if you like, on the surface. So if this is a sort of a three-dimensional balloon, assume that you've got a hole on the surface of this balloon. And we're going to call that dA, which represents a small segment or a small cross-sectional area of the surface. This n is the outward pointing unit normal vector, which this is actually perpendicular to that opening. So whatever that orientation of the opening is, n really represents the normal vector on that. It's a unit vector. And you've got the pressure. This could be the internal pressure in this balloon. Let's say like 5 psi, 10 psi, whatever that is. And by increasing the force, or actually pressure inside the balloon, you know that this balloon is going to expand. And if this balloon is going to expand, then something's going to happen to dA, because dA is going to grow. If you imagine, if you draw a circle on the surface of the balloon, as you inflate it, this circle would grow. And of course, the volume of this sphere or this balloon is going to increase as well. And any change in any of these parameters will be defined as dF, dV, and then we use d essentially to indicate that change. Okay, so let's look at the mathematical representation here, starting with the fact that change in force is pressure, whatever the pressure is inside the balloon, times the change of the cross-sectional area. And that is something that you know anyway. Force equals pressure times cross-sectional area. Now, what I've done here, I have replaced, so I've kept P because P is just pressure. I'm not going to change that. What I have changed is I have replaced dA with nDA. And mathematically, I think you've covered that when you're dealing with vectors. You can now replace something which is a vector in this case, replace it by n times that change in area. Now, I'm now interested to go to work and look at the equation for work. Now, again, note that I've used delta here because This is work is not a property, as opposed to force, which is a property. And I've used the dot product, F and U. And based on what I've already done here, I'm going to replace df by so I'm going to replace df by pn dA, and you know that from here. And then what I can do, I can then relate the change in volume by these three parameters here, as is shown here. So the change in volume for that cross-section area, dA, is really n times the change in the displacement times the area. And that is actually a very useful equation, because that would lead to something extremely important. And this is the equation, which you also have it in your formula sheet, and you're going to be using a lot, because based on what we've described here, you can replace, or you can find an equation for the work done, and this d here again represents displacement, because I'm talking about displaced work, I'm not talking about any other type of work, and it's simply pressure times a change in volume. What you've seen here was a derivation, so I can't just give you one equation and say this is the equation, just use it. This is how this equation has been found. Am I going to ask you to derive this equation? Probably not, but it's useful to understand where it comes from. Let's just look at this example in the piston and the cylinder. If you start with the initial pressure and temperature, and then you start to increase the pressure, for example, and then assume that you move by du, that's the amount of displacement. And of course, this is, if this cylinder is three-dimensional and maybe circular, then you can assume that this du has 3 dimensions, and it just looks like it looks like that from the side, but then it's really a circular shape like this. Sorry. This is actually the change du in terms of volume. So the equation, what we derive in this case would be pdv, and dv is nothing but change of displacement multiplied by the cross-sectional area of the cylinder. Let's now do one example, and then this makes more sense. I've got 2 examples here on the next page. The first one is actually quite straightforward, so I'm going to skip this one. I want you to do this in your own time. Self-study. I'm going to move on to a more complicated one. So, again, we're dealing with a spherical balloon, which is now being inflated, and the radius changes from 0.1 meters to 0.2 meter. During this time, the pressure is found to satisfy pressure proportional to radius to the power of 3/4, where r is the radius of the balloon, and the volume of the sphere is now given by this equation. This is obviously a universal equation for the volume, not only specific to this question. What you need to find is, first of all, to show that this is how the work is calculated for this case. and then it asks for a number of things. The last thing is actually show that there's a constant which relates the pressure to the radius, and that constant is this value. So let's just do this very quickly. The starting point is this equation, what we said. This is a displacement problem, and of course you have to start with delta W equals PdV. Now, because we know that according to what the problem has, we already know, if you start with the with V, if I say what is dV dr, then you just have to differentiate this equation, and you end up 4 pi r squared. So by doing that, we know that dV is this times dr, and that's actually what I've got here. So I can simply replace dV by this equation. This is what I've done here. And all I need to do is now to integrate this equation. And of course, this is what the question asked us to prove. So you work by moving from this subscript here. If it's not clear, this is moving from point 1 to point 2. So point 1 is the initial state, where the radius was 0.1, and the second state is the end process, or the end of the process, which the radius was 0.2. And this really just is a convention that we use to say that the work by moving from step 1 to step 2 is this much. Now, this is not done yet. We need to use the information which we had, and then this is the key information here. This is how we know the pressure is related to the radius, and we're going to use that information now. So P is proportional to R to the power of 3 over 4. Of course, that doesn't mean that it's equal to R to the power of 3 over 4. It means that it's proportional. And what I can do is I can just use a constant. Let's just call it K. And it would be useful just quickly to do some dimensional analysis. This is dimensional analysis. Similar to what I was doing last week, and I mentioned about finding the units of different properties and different equations. And simply we're just saying that the units for pressure is Newton per meter squared. And on the right hand side we've got K, and the unit for radius is meters. So it's meters to the power of 3 over 4. And therefore if you were to find the units for K, it would be Newton over meters to the power of 11 over 4. And you can see how I've got that. When you multiply these two meters, then that's what you end up with. And you'll see why actually this is useful in the next equation. So the next part, I need to come back to this equation now, and I need to replace P with KR 3 over 4. Now, that's what I've done here. If you actually replace P with this equation, and then, let me just zoom in so that you can see more clearly. If you replace this with this, and then if you start adding up the powers for R, you end up with R to the power of 11 over 4. And of course, you can take the constants out. 4 pi k is a constant, so it comes out. And naturally, you do the integration here. If you are struggling to understand how you end up from here to here, I'm just going to do a small side note. I know most of you would know this, but here, let's just, in a simple case, let's say we've got 11 over 4, that's R, dr, and that would be 4 over 14 r 15 over 4 plus a constant. And this is just to tell you how this has been calculated. So I'm just going to leave that again. And once you do the integration, you just have to put the values in there, R2 and R1, and you end up with this equation. We still haven't put the constants, 0.2 and 0.1, in here, because there's still one last step, which is inserting the value of the constant. Now, we know the constant is given to us. This is the value of the constant. And all you need to do now is to put that in here, insert the values for R2 and R1, and you end up with the value of the displaced work in kilojoules. When you, this is, I think, just a point of on practice, really. In the tutorials and in the exam, I think it's quite useful when you find the final answer, always try to underline it, and also make sure that you've put the units there as well. It's very important. You might find the right value, but if you don't use the right unit, then you're not going to get full mark for that. Any questions on this example? Okay. So, next page. This is your favorite part. We've got two more examples of a surface. So it's another type of work which is on a surface, and also the other one is on a turbine, which has applications to turbo machinery. Now, this is, guess what? This is optional. Yeah, so lots of derivations. And of course, I encourage you to go through those because they are useful, but not as far as the exam is concerned. Something else I just want to mention, this is the last thing before we stop, is that this table is actually quite useful. So, guys, just bear with me for a few more minutes. When you've got different types of work, and we saw some examples today, actually. We saw linear, and we saw displacement. I skipped, for example, the rotational one, which was the turbo machinery example, and the stretching, which is the surface. And now these two are actually far away from it's beyond the content of this unit. But what I would like to say is that there is some similarity between these type of work, and they all actually fit in this type of equation. So in general, the change in work is equal to force, or something equivalent to force, times something equivalent to displacement. So this represents Fk, and this represents dxk. And when you look at different situations, all it's changing is really those parameters. So because we are only using this two and this two, and in fact actually we use this one more than anything else in thermodynamics in this unit, this just shows that this is only one type of work, but it's an important one as far as we're concerned. But the rest can be actually fit into this generic format should you wish. And from that point of view, this table is actually quite useful. But apart from that, we're going to stop here, and we're going to carry on a very important topic, polytropic processes, next lecture.